Today, we will talk about the network coupled measured games and how we solve that through spectral analysis and the associated network centralities. This presentation contains a joint work with Peter Keynes, Mi Huang, and the Renewable Chandler. So I want to start with the motivation of looking at networks of dynamical systems. So we see many examples of network ranging from social, biological to technological networks. These networks have the features that oftentimes a node is associated with a state that characterizing the status. And the states interact with the states of other nodes, so they evolve together. And there could be times their nodes are associated with cost. And the cost could be coupled and hence leads to coupled decisions for these networks. And most importantly, this network has the property of heterogeneity, which means that you look at the connection neighbor of one node that could be very different from the neighborhood of other nodes. In general, when we look at these systems, they are complex due to the following reasons. First is the large or growing size of these networks and the complex coupling structure of the problems that we are looking at. And oftentimes the network or the underlying dynamics are uncertain. And moreover, there could be different form of nonlinearities on these networks. So for the presentation today, I will only focus on the aspect of large and growing size. And the way we deal with this is to employ the theory of graphon. Give us a model to model large graphs, graph limits, and the random graphs. There has been application of the graphon idea in various problems, such as the heat equation, coupled oscillators, the mean field particle systems, and people have been using graphon to look at the static network games, where the network is very large. Look at dynamic games, in particular, the work of graphon mean field game initiated by Shuang Gao. And the control of network coupled dynamical systems, network centralities, signal processing, graph neural networks, and epidemic models. The context for studying mean field game on networks can be very different depending on one's definition of the underlying network. Whether it's interaction in the states, in the cost, whether it's constraints on the underlying state space. So there are different formulations. I list some other works here with different type of formulations. Probably the first one start with the work by Shuang Gao in 2010. So I will talk about one particular situation where we call it the network coupled mean field games. So I want to start with the notion of graphon. We look at the graph. We represent the connection by the node and the link. And we can also represent the graph structures through the so-called adjacency matrix given here, where the ijth node has a value 1 if there is a connection. It's 0 otherwise. If we embed this adjacency matrix into a unit square, we think about this as a picture where each pixel has set length 1/n. Okay, now we have a new representation of adjacency matrix and hence the graph. And this adjacency, this new picture has the property is actually a function that mapping from 0, 1 square to 0, 1 interval. If the underlying graph is undirected, then this will be a symmetric function. Now with this new representation, we can think of graph of different sizes. We can compare graph of different size, and we can look for graph sequences and then identify the corresponding limit if the limit exists. So of course, the limit exists under a proper metric when you compare the distance of different graphon objects. So, but formally, graphon is defined as a symmetric measurable functions from unit square to unit interval. Now, if you look at any finite graph, because of this construction, you see that any finite graph can have a graphon representation. It is a special case of graphon. So any of the results that we discussed here will automatically hold for finite dimensional graph. So this will be, when we look at graphon, this will be a generalization of graph where that can include the graph of infinite size. So the study that have been carried out is using graphons in studying control problems of network of linear systems. This started in 2017. And then I've done a set of work on graphon mean-field games. In the case where it is linear quadratic, we have analytic solutions for these cases. And I want to emphasize the graphon mean-field game work is initiated by Keynes and Huang in series of papers starting in 2018, and where they look at more general case, a nonlinear case, establish existence of uniqueness of solutions and the approximation error bound. So the idea of using graphon to study these problems is illustrated over this picture here. We start with a network which is finite dimension. It could be large dimension. It could be the network has uncertainties. So the treating the problem directly at this level is quite complex. So we look for an approximate solution. The approximate solution we generated through by looking at the graphon limit. Use the graphon limit, generate a strategy, and then apply that strategy to the finite network. So for this methodology to work, we need to answer the following questions. The first question is the convergence. What do we mean by the finite network converge to a graphon limit? And second question we need to answer is, once we reach the graphon limit, how we design control? How do we synthesize strategies? And we need to ensure that the way we make synthesis is scalable, because here actually the number of nodes is already infinite. So we don't want an infinite complex problem. And when we apply this strategy to the finite network, we need to give some form of performance guarantees. And these questions are answered in various ways in the work that I listed here. So here is an outline of my talk today. I will give you a more concrete illustration and discussion of the spectral properties of graphons. And then we will launch on a particular case where we look at the linear dynamics, quadratic cost, Gaussian noise case for the graphon mean-field games and how we apply spectral analysis to it. And this actually leads to the study of fixed point centrality for networks and graphons. And I will talk about the definition of this and the property of the centrality. So as we mentioned, we look at the symmetric measurable functions that map from the unit square to some bounded interval. In this case, I use it minus c and plus c, denote that set by WC. Okay. The first thing we need to look for is the definition of norm, the size of the object. Here, this is called the cut norm, where we look at a source set and a target set. And by this integration, we are looking for a cut between the source set, node set, and the target node set. And we want to maximize this or synchronize this over all the possible choices of source and target nodes. So this identifies the maximum cut for the graphon object. Now this is just for one graphon object. If we want to compare two graphon objects, we need to introduce something a bit more, which is this notion phi here, which is a measure preserving bijection, which in the finite graph case is just a relabeling graph. So you look at the graphon, you relabel its index, and you put the relabeled index into the original graphon that generated the same value. And when we compare two graphs, we want to make sure we compare them with the best possible choice of these relabelings. So we take an optimization over the relabelings that gave us the cut metric. One important property of the graphon space is that under this cut metric, the graphon space is compact. which means infinite sequence will always have subsequential limits under the metric, and the limit stays in the space. So it's meaningful to talk about the limit object. Now, graphon can be used as operators. In particular, it can be used as operators from L2 functions to L2 functions. And the operation is as follows. We have an L2 function here, and this is the graphon. We take the convolution integration with respect to the intermediate variable that produce output at the index x. So this, you can make similar analysis to matrix times vector. And then in a similar way, one can define operator products where we do the integration over the intermediate variable set for two graphons. This is the analysis to matrix products where you take two matrices. And then there is a useful relation between the norms, because for graphons, we can choose different norms. Some are convenient to work with, some are not. We started with the definition of the cut norm. It can be shown that it has a nice relation between the cut norm and the operator norm. And here, the operator norm simply is the L2 operator norm. And from now on, we will work mostly with operator norm because it's easy to characterize.
So sorry. So what's the intuition for the operation of the functions? So what is it when you apply a graphon to a function?
Yes.
And so you start with a function and a graph, let's say.
Yes.
And once you apply a graphon, you get a new function. But is there an intuition of
this one? You mean this one?
This operation, the first one.
The first one. So this, you can think of it as vector in the L2 space. This is a linear operator.
Yeah,
basically this was you have the input at this index, then you do a summation here.
No, I understand the algebra. I'm just asking about which, like, physically, what would you use that to represent what? Like, say, I can see that I have a function and a graph, so a number of people at every location.
Yes.
And I apply a graph onto it. It looks like this operation is sort of like maybe pushing mass to edges, or like.
I think you were thinking about the optimal transport.
I'm trying to understand what this operation would be good for physically. What it could represent.
I mean, this basically means a weighted average of whatever we have input into a weighted average that produces an output.
So at each node, I do an average of the nodes around me.
Not yet. So this is just this is the value at the node alpha.
Yeah.
And this is the weight assigned between node alpha and node x. And I do the average, weighted average of all the. It's like exactly
so
the same.
Like in say graph signal processing, there are also versions like that.
Yeah, they call it what is it? Graphon sync operators. Yes, they use it.
So it's like a filter. It's like a filter on the function that takes values on node of the graph, and then you can apply different filtering operations. So this is just a filtering operation.
Yeah, you can think of that. This is a linear filtering. So when you use it as an operator, it has a very nice properties. Graphon has operators. They are Hilbert-Smith operators. So they are then compact operators, which means they can have discrete spectrums, which means we can write the eigen decompositions very nicely. And the number of eigenvalues is infinite. It could be finite or infinite, countably infinite. FL is the eigenfunctions. And we immediately see that the eigenvalues accumulate at 0. That is because when you check the L2 norm of the graphon is bounded, which means the sum of the square of the eigenvalues goes to 0. So you see that shrinks to 0 is quite fast. Now, when you look at the graphons, they can either be approximated by finite rank representation or can be characterized exactly by a finite rank graphon. I gave you some examples. First example is the Adolphe graph, where this is a graph model that you generate a random graph by connecting node pairs with probability P. In the limit, this graphon is very straightforward. It's just a constant area. Here I plot an example for a network generated using this model with 100 nodes. There is connection probability 0.5. And this is the corresponding step function representation. You don't see a structure there, but when you look at its spectrum, it's striking is that you see there's only one eigenvalue that separates itself from the rest of it. And it's also illustrated here. So the point is that the limit of this model is simple. It's because the eigenstructure is simple. It is a rank one graphon. Now another example is the uniform attachment graphon graph limit. Here I show you this picture before. This is a process where you construct a graph, grow the graph at different steps. Each step you add one node. At step K, you connect non-adjacent node pair with probability 1/K. And then you can identify sequences of graph. And this graph converts to a limit function. The function is 1 minus max x1. We look at except the edge and elsewhere is smooth. And through an exercise, I identified, okay, this has a very nice spectral decomposition. The eigenfunctions are just cosine functions. And the eigenvalues shrink at the speed 1 over square root of 1 over square K, where K take odd numbers. This means that if you take the first eigendirection, the approximation error is less than 1% in operator norm. There are other examples, mean field coupling, multi-partite coupling, idempotent coupling, stochastic block models, and some real-world networks that are either exactly characterized by low-rank graphons or approximated by low-rank graphons or low-rank graphons. One last ingredient on the properties is the property of invariant subspace. We start with Hilbert space, and we look at the linear operators on this Hilbert space. A subspace in a Hilbert space is called an invariant subspace of that linear operator T if for all the elements in that subspace, after mapping using this linear operator, it stays within the space. It doesn't go out of space. And such a space is sometimes called a T invariant, where T is the linear operator. Immediately we see the examples. Any eigenspace of the graphon is M invariant, where M is the graphon, and the kernel space and the orthogonal complement space are M invariant. And M and the polynomial functions of M, they share the same invariant subspace. These are just properties that are useful when we explore these structures. We can identify low complexity solutions for our problem. So, and now I want to move on to the linear quadratic graphon mean-field games. It's a scenario where agents, you look at the large number of agents, say capital N number of them, and they are competing against each other in the sense that they have their own individual cost, they have their own action, and this is the own strategy. This is the strategy of everyone else, and they are coupled through a network M. And they can have their own state dynamics. Their xi is their state, ui is their control. They are coupled over a network. Each individual can have a noise, independent noise. So for these problems, we need to look for Nash equilibrium as the solution concept, which is defined as a strategy N tuple. If we have capital N number of these agents, each of them has a strategy. If we assign the strategy to all the agents, say we assign it, and if an individual agent wants to deviate, he has no incentive to deviate because it will incur a higher cost. And then if this property is satisfied for all the individuals, we call this as a Nash equilibrium. So the issue with this solution at this stage is that the complexity of identifying the equilibrium skills increases with respect to the network size. And the second complexity is that you always need to know the exact network structure. So the solution idea of using graphon is just to figure out what are some approximate Nash equilibrium where the network are represented by the graphon limits. Okay. And the questions one can answer include the well-posedness, existence, uniqueness of Nash equilibrium. And when you apply this equilibrium on a finite population, you need to give some performance guarantees of the approximation error. And for linear quadratic case, we can identify solution methods which are low complexity based on subspace and the spectral decompositions. And for a particular class of infinite horizon problem, we can give explicit representation of the equilibrium cost. I want to also mention that the first aspect for a general nonlinear system is addressed in the work by Keynes and Huang in their series of papers. So you should look for that if you're interested in the more general case. Here I'm only presenting the case with linear dynamics and quadratic cost. So here is a more concrete illustration of the problem. So we look at the population of agents, and they are interacting over a network where each node on the network could represent a population. For an agent that's sitting in the population queue or cluster queue, its dynamics is as follows: has its own state, its own control, and some network couplings and their Brownian motion noise independent of different agents, and also independent of with respect to the initial condition. And the coupling here has this particular structure. First is all the nodes that are sitting at the one node, all the agents sitting associated with one node, they take an average on that particular node. And then they do a network weighted average to produce this influence vector setup. And the costs are coupled in the following way, where individual want to track some affine signals that are the underlying affine functions of the underlying Z products. Here Z, I call it the empirical network average, because first you take an average and then you take a network weight. And the individual agent want to minimize this cost using small control efforts. So we have a quadratic cost in the control effort as well. I want to also mention, emphasize the feature here is one node, one population per node. In fact, the notion of node could be features. When you think about it, these are users, these could be users with the similar usage profile, similar behaviors, and similar types. And when you think about this as an epidemic model spreads across cities, then each node will be a city. And when you think about the neuronal dynamics, each node could be a bunch of neurons that have that work simultaneously together, or they share the same properties. And in social system, you think about community structures, this will be then one community. I think when we look at this averaging effect at a node level, it has the benefit that individual states is no longer visible when you're simply looking at the average. So sharing this information from node to node kind of mask individual state information. This can, I think, is useful when you think about scenarios where privacy of your state is important. I mean, the example we see that over epidemic spread over cities, you don't want to share the individual information, but you can share the population level statistic. But the population level, of course, you look at different cities. The different cities have their own different statistics. Okay, so now go back to the problem. We can use the standard mean field game idea is to take the population limit. We let all the population at different nodes, all the nodes goes to infinite. At all the nodes, you have a different population, let all the population size go to infinite. What happens is that we look at the network empirical average, it becomes the network mean field, where when we take the local node population average, taking to the limit, this becomes a deterministic process, and the individual state contribution doesn't matter anymore. And this leads to the network mean field, where you average this mean field over the network with the weight and 12. So this then for individual agent alpha in cluster Q, when he looks at the problem, this becomes a problem with no couplings, because these are just some priori given trajectories one needs to follow. And this is then a standard linear quadratic tracking problem, and we know very well the solution. The solution is of this following form, where the first chart involves the state feedback. You have your state here, and the state feedback in pi t is given by a Riccati equation. Matrix ODE with second order term on the right hand side. And there is this as Q bar T here. This is the external process that depends on the network mean field. And this can be characterized through two sets of equations. One is the equation ODE moving forward in time, characterize the network mean field evolution. And second equation is the backward equation characterizing the offset process. And note that these equations are coupled, because on the right-hand side of this equation, you see the process S here. And this equation on the right-hand side, you see Z. So they need to be solved together. So now the problem, if your network is small size and you know exactly the network, this is kind of where you sit and you can stop this is a complete story. But when you look at the network in cases where you don't know the exact structure, you don't know the exact weight, then you need to figure out the approximate solutions. Also, when you look at the case where the network, look at each of these equations, they are dimension small and capital N. So if you have these equations are large dimension, small n is the state dimension for each individual agent, and capital N is the total number of agents. If the product is large, so you need to figure out ways to reduce the complexity. So we use the idea of graphon approximation. We look at the linear control system. We represent the network interaction through the step function graphon that we explained earlier. And we use the same type of partition to identify an equivalent representation of the vectors, the L2 function, piecewise constant L2 function, and same for the control. Now we can identify an equivalent representation of the same system as a graphon system. Now, if we have limit objects for graphons, we can identify limit equation. And the finite system converges the limit system in the sense that their solutions converge. This, of course, will be under conditions on assumptions on the convergence of initial conditions and the convergence of these graphons. So this is a more concrete representation of the process that we developed earlier. So we have a forward equation, backward equation. Forward equation characterizes the graphon mean field, network mean field. You can write it in the graphon ODE form, and the backward equation we can write in infinite dimensional ODE form. And if you replace the object by the limit object, limit function graphon, then we have a limit representation. Now, to solve these equations, that involves the standard step of constructing a fixed point map. You write each of these differential equations in the integral form, and you class S into here using the integral form, and identify a condition that tells you the fixed point map is contracting, where the fixed point map simply that you can start with a process Z, for example, and you put the Z here, you plug into this equation, you solve for S, and then you plug in S here, you solve it for Z. So you construct a map that you start from some S, and you map it back to an S. So this is a fixed point map in a Banach space of continuous functions. So we only need to identify the contraction condition to apply the Banach fixed point theorem. In fact, this is the condition of the characterizing coefficients that we need. If this coefficient, which depends on the underlying graphon limit, if it is less than 1, then the mapping we have is a contracting map. So then there is unique classical solution here, where these are just continuous functions over time. And when you evaluate at each time, these are L2 functions. Now, we already give you an idea how to solve for an approximate solution for the offset using graphon approximation, where we construct the forward graphon ODE characterizing the graphon mean field evolution and the backward graphon ODE characterizing the offset process in the limit. And we use this as a fixed point map. This generates the offset process as in the limit. And this can be used as an approximation where you put in your equation that you initially look for the best response. So this will be an approximate best response for finite agent and finite node case. So there can be two types of approximation results, depending on what you're looking for the criteria. One way is to look at the graphon mean field in the limit, and this is the empirical network average. You look them as continuous functions and you compare the distance. And this distance is of the following order. It involves several terms. The first term is the difference between the limit object, graphon, and the finite network in the operator norm. And the second term is the difference between the initial conditions for the limit equation and the finite equation. And the last term is 1 over square root of the population size, the minimum population size. So here is an illustration. When you increase the number of nodes, you see a decrease of the approximation error. Another type of approximation result given by Huang and Keynes is the so-called Epsilon-Nash property or Epsilon-Nash equilibrium. Yes, so the strategy you generate here is not going to be a Nash equilibrium. So individual agents still can deviate, achieve a smaller cost. However, the gain that you get is always smaller than the epsilon, where this epsilon is a small constant. And it's shown that here the epsilon goes to 0 as the number of nodes goes to infinite and the population, minimum population size goes to infinite. Okay. Now, in terms of application, this is then the key point is to figure out the solution for this equation. Once we figure it out, we kind of have a very good approximate of the offset process. I recall these two equations to give you an idea. And here is this graphon forward equation that you see graphon couplings over here, graphon couplings over here. For the graphon backward equation, there is no graphon couplings. And the idea we solve that equation is we look at the process X, we project it into the eigenspace, space spanned by the eigenfunction. And the rest of it is just some invariant subspace orthogonal to the eigenspace. We do projections for both the process S and process C. If we do that, it turns out the solution can be separated into two corresponding parts. One is the eigenpart, and one is the part associated with the orthogonal invariant subspace. And the property of this is that now when you look at this, you can separate the space variable and the time variable. Same here, you can separate the space variable and the time variable. And the same for the offset process for the graphon mean field Z. You can separate the space variable, index variable, and the time. There is no Z rev term because you can verify that it's actually equal to 0. And these coefficients here, these are finite dimensional objects. They come from a set of ODEs. One is the SL. This corresponds to the projected value in the L's eigendirection. And this is the projected value in the L's eigendirection for Z. These two equations need to be solved together. And this equation is simply a self-evoluting linear ODE. So this can be pre-computed offline. So now we turn a problem that we start is infinite dimensional, we'll turn it into a problem where we solve the number of these equations and one this equation, where B is the rank of the limit graphon. Now one can also find solutions use the decoupling operator Riccati equation. This is just following standard approach of decoupling these two equations by introducing a new Riccati equation. It's just like here the Riccati equation, all these coefficients, these are just L2 operators mapped from L2 function to L2 function. We showed that if the contraction condition holds, then this operator Riccati equation will have my solution. And if the Riccati equation has a solution, can also show that the equation for S and Z, they have a unique classical solution here. So the way we apply this operator Riccati equation is as follows. We first introduce an offset error process E that characterize the error between the S and minus Z. Okay. And once we do that, we realize that this equation, the E process satisfies this ODE. It's a self-evolving ODE. So this can be pre-computed once you get the solution for E. And then once you get that, use this relation, one can identify a representation between S and Z. This is known. You do this representation, you put this into the equation for Z, this become a decoupled equation for Z. You solve for the Z process, you get the function, the trajectory Z cross. And similarly, you plug in Z cross into the equation for S, and you solve for S. So you, in a decoupled way, you solve for the pair of trajectories, Z cross and the S cross. These, as I mentioned, follow standard ideas that's used in linear gains and optimal control for decoupling two-bound boundary value problems for linear problems. And now the question, there is another remaining question. How do we get this P? These are infinite operator, infinite dimensional space of objects. So it turns out under assumptions for our problem, the solution has this unique structure. The operator Riccati equation has two parts. This part is an identity operator part with a coefficient, and this part corresponds to the eigenspace part with another coefficients which are different for different eigendirection. And this equation P perp here is just a ODE, linear ODE. And this PL, that these coefficients in the L's direction, is another Riccati equation, which you see the second order term on the right. So this turns into the problem of solving the operator Riccati equation into the number of Riccati equations, each of which is n cross n, where n is the state dimension of your local state, plus one ODE n dimension. So this depends on the choice of your graphon limit. If it's a low rank, then this is the gain, and you have a simple problem to solve. Okay. For the infinite horizon case, where the individual cost is discounted by some discounting factor, where the rho is a positive constant. So you look, you value your cost at the moment more compared to the cost in the future. And with dynamics that does not have couples in their dynamics, and the individual nodes can have different individual nodes. Now with this, we can have a closed form, explicit representation of the equilibrium cost. The first line, this part is something characterize the individual nodes, and the second part is like a graph filter, where you look past the signal through the eigenfunctions, and to each different eigenfunction direction, you have a different value for it. And then additional to that, there is a cross-coupling terms between the different eigendirection K and L. These are second order terms. This is natural because when we look at the cost structure, it's squared, so that automatically we will involve these two summations across different eigendirections. So this is just an illustration for some particular structures. If you have a cosine graphon, you plot it here, you can immediately draw the curve for Nash values. And when you look at the uniform attachment graphon limit, you could do things. Now, up to here, it seems like these Nash values do tell us something about these underlying graphs. And so the question that we ask is, can these Nash value for dynamic beamsform network help us to characterize the importance of nodes on the network? So this leads to the discussion of fixed point centrality. I will start with the notion of centrality. You can think of it as a mapping from the node set to analytic numbers. It's quantified the importance of nodes on the network. And here is an example. You give each node a different value, okay? And then you rank the nodes according to the values, and then you identify the important nodes. These appear on top. Okay, so this has been used to study important nodes or social influence on social network. This can be characterized by the eigencentrality. The quality of websites can be modeled by the PageRank centrality. And the equilibrium actions in static network game, where the cost has this linear and quadratic structure, is shown to be proportional to the Carlson-Bunassi centrality. There are other application scenarios, but I will just focus on these three because it's relevant to the definition of fixed point centrality. So the eigencentrality, you look at the network structure, you look at its largest eigenvalue, identify the largest the eigenvector associated with the largest eigenvalue. That is a vector which assigns each node a different value, and this is simply the eigencentrality. And the Bunassi centrality is that you look at your neighbors, and you do a weighted average of your neighbor's centrality value, and plus some offset, and this produces a value for yourself. So this means my centrality depends on not only the number of nodes I'm connected, but also depends on the quality of the nodes that I'm connected. And the other interesting example is PageRank centrality, where you look at the nodes as a web page, and the links Aij equal to 1 if there is a hyperlink from node I to node J. So now individual surfer come to the net, and they were standing at node J, they were just randomly choosing with uniform probability the link, hyperlink on the network. And this gives you the centrality for node I. Of course, this will be some offset process that ensures the problem is well posed when the network is very sparse. So all these centralities, when you look at them, it has the feature that you start with some value, you map into some value. Start with some value, you map some value. So this is a fixed point structure. This is very similar to the solution structure we looked for solving RQG graphon equations. I want to also mention that this PageRank centrality is actually the steady state distribution of a random walk on a network, where the network is the hyperlink structure of the web pages. So now we want to use that as a motivation, as an initial step to look for a centrality that can characterize a larger class. But we need to pay attention. This centrality that we discussed here, the value only depends on the graph structures. So we want to construct something that imitates that. And this is the property of permutation equivariance. When we look at the map that takes the matrix and the vector as input, produce a vector of the same dimension, we call such a mapping permutation equivariant with respect to the permutation mapped by if we permute the input. It's equivalently that we permute directly the output. The resulting output is equivalently permuting the output of the original. If this holds for all the pi's, permutation equivariant For all the pies, which are the permutation maps, then we call such a mapping as permutation covariant. Okay. And with that, we can launch on the definition of fixed point centrality, which is characterized by two maps F and G, which are permutation equivariant. The XA is the features, and the dimension of the feature simply follows the dimension of the nodes, for the dimension of the number of nodes. So this map F summarizes the network into features XA, and then G, the map summarizes these features into a real value that tells you how important nodes is. And with this, we see that the page rank, eigencentrality, correspondence centrality, and the Nash values for the game that we look at, they follow these definitions. So under technical assumptions, one can identify the convergence of the centralities with respect to the convergence of the underlying matrix of graphs. And here, L1, LG, L0, these are just some Lipschitz coefficients for function f. Here, the norm, you can choose arbitrary norm, as long as it's compatible with the orbital norm you choose here. The implication of this is this means that convergence of graph would imply convergence of centralities. And second, if you look for graphs that has uncertainties, we can identify approximate centralities by looking at the limit centrality. So this is just to say that for LQG network coupled medium games with homogeneous initial conditions, this is actually a fixed point centrality where the feature is not a vector, but is at each node the feature is just a continuous function. Is that the graphon mean field? Okay. And this works for graphons. The generalization is immediate. We only need to figure out the suitable space for these features. Choose LP, for example. So one can immediately identify the similar type of results where the centrality in LP norm is bounded by the different these operators in the operator norm. The same implication holds here. Interesting thing is that when you think about page rank centrality, it is the steady state distribution of random walk on a network. So the centrality can be related to probability distributions. If you want to think of a centrality that way, then you may want to compute the difference between the two centralities in the distance that is for characterizing distributions. In this case, for example, the Wasserstein metric. You compare two distributions, and it turns out this can be upper bounded by the cut metric, where remember the cut metric also have this optimization over there. Okay. Now, this is an illustration of as we increase the network size. This is the convergence of the centralities. This is for a problem on infinite horizon, QT graphon into games on a uniform attachment random graph. So these are small graph size. As we increase the network size, you see the convergence of centrality to the link centrality. Now one can look at a comparison with the standard centralities such as the degree centrality and eigencentrality are listed here. These are the figures for eigencentrality and degree centrality. These are the blue ones are the Nash value for the fixed point centrality for LQG graphon nodes. And you see that another line here highlighted in the box. These are just rank 1 approximation of the length of them. You see a flip of the directions of these functions. It depends on the scenario you're looking at. If you're looking at the reward instead of cost, you will have something quite similar to that. And the last thing that is the introduction of a customized value for each node. Because for LQG graphon input games, you can associate each node with a different initial mean. This gives preference to different nodes. So you can define customized centrality, similar to customized or personalized page rank centrality. But you see that This would significantly change the landscape of the Nash values. Instead, you get a minimum point instead of you minimum point on point. Okay, so to summarize this talk, I present to you the spectral analysis of graphons and how to use that in studying QG graphon-mediated beams. And then afterwards, this leads to natural definition of a centrality, which we call fixed point centrality. So for further directions, it's important to look at the sparse graph limit models and how that can be used in the games and in centralities. And to look for, investigate the connection between the fixed point centrality, graph neural networks. In fact, when you look at the initial paper on graph neural networks, the idea is constructing a fixed point map where it creates the features for individual nodes. This fixed point centrality seems to be a special case of that, where one only look for structural properties. You do not look at the properties that are associated with each node labels. And this, of course, will be related to multiple decision processes in infinite horizon case where you solve for a fixed point. And another interesting question is to look at the ranking variations when we do network modifications. If you change, remove link, how does the order of the, how you will rank the nodes change? And another direction is looking at Mayfield games over networks, where the networks here, as I mentioned, it can be broadly defined. And we'll have completely different type of dynamics. So the scenario for application I'll be looking at is renewable energy systems, transportation system, and the epidemic threats. So and others. So that's the end of my talk. So thank you.
Thank you, Shuang.